discussed last time on the concentration polarization phenomena. We discussed about concentration polarization in pressure-driven operation, reverse osmosis, ultrafiltration, microfiltration. Remember that this kind of phenomena is present in any membrane operation. They can be different in mechanism, they can be different in the kind of phenomena, can be related to concentration polarization or temperature polarization, but there is no membrane operation in which we can neglect to consider this kind of problem at the interface. We will discuss also in electrodialysis, in fuel cell, for example, that sometimes people don't consider. We always have phenomena at the interface which can be very, very significant and killing the efficiency of the process if you don't try to control them. We saw that this system can be analyzed in different ways. There are some approximation when you want to try to solve the problem, and the traditional approximation is to consider that the film theory, in which we are assuming that we have a kind of stagnant film formed at the interface, and just only the certain distance we will have the traditional bulk concentration. In this region, we will have a linear change in the concentration in the thickness of the boundary layer. The equation, by the way, we already considered that this kind of problem can affect significantly the performance of your membranes, for example, changing the transmembrane flux significantly. And the experimental results, for example, are showing you that if you just change not the pressure, not the driving force, but just steering, just mixing better the solution, transmembrane flux can change significantly. So without changing membranes, without changing driving force, the effect of the transmembrane flux can be very different depending on how you control interfacial phenomena. That's a typical example and telling it. By the way, this is the effect in terms of transmembrane flux. But keep in mind that when you are forming film at the interface, also the selectivity of the membranes can be modified. So it's not only the transmembrane flux, but also the overall performance of the membrane, including selectivity, that can be totally different. So these phenomena are quite important, and we have to learn how to control them. We just discussed already that if you just neglect any problem related to the osmotic phenomena, that means assuming that the formation of the boundary layer and eventually the formation of an additional film on your membranes, physically you can have the formation of a gel or a cake layer, and you can assume in a first approximation that the osmotic pressure eventually can be neglected. This additional phenomena, the additional film, does not affect osmotic pressure, which is an approximation, cannot be real in many cases. But if you make this assumption, you can rewrite the relationship between the driving force and the transmembrane flux through a term of proportionality that we know, and the different resistance that we are creating in our system. So the initial intrinsic membrane resistance, the one that you can measure doing experiment just with fresh water, with no salt, so no concentration polarization phenomena, this term has to be considered modified by an additional term, the initial resistance, related to the thickness of the film that you are going to form, and that explains the effect of the steering that can reduce the thickness, and the intrinsic resistance of this additional film that we are going to create. This is a relatively simple equation, similar to some of the equations that people were using in traditional filtration system, Darcy law modified, and on the basis of this kind of equation, you can recalculate the transmembrane flux and predict the interfacial concentration, etc. The only thing they have to consider that if you relate to the initial membranes, when there is no cake formation, no gel deposition, the new membranes is this one. So you are just creating a new membrane where the intrinsic resistance Rm that we saw before is no more the initial one, but you have this additional film here. In this case, again, you can neglect osmotic phenomena, but this is an approximation because the film that you are forming here can have some much more rejection, for example, also for some of the small components present in the solution. So the initial film, if it was microfiltration, ultrafiltration, had no osmotic problem to be considered because everything was going through. But when you create something new at the interface, this something new can have some selectivity, rejection, also for some ions. So in this case, you can have an additional phenomena of increasing the concentration of the ions. You can create this new concentration polarization, which is different from the initial one, and this can have osmotic effect. This seems to be simple. Many plants have been installed years ago in ultrafiltration, for example, that were not running correctly for this kind in the dairy industry for this kind of phenomena because people were not able to predict the selectivity that this kind of gel formation related to some protein in the milk ultrafiltration were creating the interface and inducing additional osmotic phenomena. So people were designing a plant producing 50 cubic meter per day or per hour, and only 20 were coming through, and it was not clear what was happening. They were changing membranes, and it was not a change in membrane. It was a question of not efficient control of the concentration profile related to the selectivity of the additional film form for related to the concentration, polarization, and fouling phenomena. So this kind of system initially were not very well understood, and is complicated to understand. For example, we will define shortly a term. When you are discussing about a solution property, you are normally talking about concentration. When you're talking on this kind of phenomena, you have to define ionic strength, which is different from concentration. Ionic strength can change the space configuration of the molecules forming present in solution. At different ionic strengths, you can have different space, different morphology of your protein, for example. And in some cases, I was mentioning linear, some cases globular, just changing the pH, for example. And that's changed completely the property of this additional layer, inducing eventually selectivity. That's what was happening in this dairy industry, where different cows were eating different grass. Eating different grass, some of the ions were totally different. People were not aware about this, and the plant was not running. So they had not changed the membrane, changing the food for the cows that were giving the milk. So a complicated story to understand. Anyway, so that is the situation. And the relationship in this case, that if assuming that you have, again, mass transport in the laminar boundary layer in an overall system, when you have turbulent flow at a certain distance from the membrane surface, relatively simple expression can be extrapolated, in which you have the concentration of the solutes at the membrane interface divided for the concentration of the solute in the bulk of your solution, and this given by the exponential of the transmembrane flux, the volumetric flux, for the thickness of the boundary layer divided by the diffusivity of the solute. This thickness is the one that is controlling the phenomena, as we saw in some experimental results before. So if you're steering or you're increasing linear velocity on the membrane surface, you just change this term, and that is changing this concentration value. Until now, we have been discussing of concentration polarization and mentioning that in relationship to concentration polarization, something can happen also in creating additional film. this is not really concentration polarization, because concentration polarization is a reversible phenomena related to the formation of a concentration profile. When you are starting to talk about cake deposition or gel layer, that is already part of the fouling. And I was mentioning to you initially that fouling and concentration polarization, we have to consider something different. However, they are different in the origin, in the mechanism, but very much interrelated. When we are talking about concentration polarization and fouling, we have one parameter that can be introduced to just make a difference between the two kinds of phenomena, and that's what we call critical flux. The concept of critical flux is, can define critical flux is the flux value below which a decline of flux with time does not occur, while above this flux, fouling is observed. So we have just, for any operation, depending what you have in the feed, and these things don't exist, it's not easy to make simulation or modeling. You have to do experimentally still today. We don't have too much experience that you can extrapolate a very general model. Any solution, dyes, juice, pharmaceutical, etc., has its own typical story because it's related to the chemistry of the solution itself. So the critical flux is the value below which the decline of the flux with time does not occur, and above this, fouling is observed. The critical flux depends on a lot of different parameters and the overall property of the solution. So for each solution, you have to learn what is there, how these interact with the membrane, etc., and the hydrodynamics. So there are more than not one single parameter. That makes everything complicated. Typical representation of what is happening in terms of critical flux and also limiting flux is if you just plot in a very general form the transmembrane flux as function of the transmembrane pressure, or the driving force that you apply to the system. If you are working with just fresh water in your membranes, and you want to just characterize the intrinsic resistance of your membrane, normally what you expect is a linear relationship. And if you don't find a linear relationship, something's wrong with your water, or something's wrong with your experiment, because there's no motivation to have any deviation from a linear relationship between transmembrane flux and water, changing the pressure, increasing the pressure, if it's just fresh water. But as soon as you start to operate with the solution, you still have, initially, you can have a linear relationship, but increasing the transmembrane pressure, to one point, you will start to deviate from this linearity. And this deviation is evidence that you are starting to create some form of fouling. Something's happening in your system. You can still increase your pressure, and the deviation will become more significant. At one point, you arrive to a point in which increasing transmembrane pressure, nothing more happens. You are at flux, constant flux. It's very important to learn about this point and also this one. This point is important because if you are increasing the pressure, that means if you are spending money in terms of energy to pressurize your solution, nothing changes in the system. So it's better to know in advance because you're losing your time and your money if you just try to increase overall pressure. There is no increasing in transmembrane flux. Eventually, sometimes what is happening is some decreasing, because if you increase too much the pressure, the kind of gel layer or cake that you have been forming can have some problem of compaction. You can densify more, and so instead of increasing, you just decrease, because not just decrease the thickness, but you decrease the morphology of the thickness. And particularly, they can become more dense, and that means less porous and less effective by the pressure. So this is an important term also to be defined, which is a question of, again, of basically the chemistry of the system. But this is also quite important, because if you are working until this critical flux, where the deviation from linearity start, this point is the point in which, if you now stop increasing pressure, and you go back, you stop your plant for starting again after 2 hours, in principle, you are supposed to have no hysteresis. That means the flux will start again from here. If you are trying to operate at a higher transmembrane flux and transmembrane pressure than this point, you have a deviation which can be significantly irreversible, which means that now if you stop at one point to pressurize and you want to start again tomorrow, you will not start again from here. You can start down here. You have an hysteresis. Part of this phenomena is irreversible. And so if you want to operate nicely for years, every time at the same level, in this range, if you know exactly the critical flux related to the pressure and the limited flux, you can well define the operation in your plant. You will be able to operate always in a same transmembrane flux, up and down, thousands of times. If you run in here, you can have this kind of phenomena, and this phenomena can be worse and worse. Next time, you can have still down here, etc. So it's always increasing because you are increasing the irreversibility of some of the fouling layer that you are creating. Okay? So that's why there is a lot of technology that you have to develop to understand this. Very difficult to predict theoretically because the chemical species that have a lot of parameters changing them, adsorption, desorption, different configuration, etc., can be done, but the cost of doing that is much more than just making the experiment sometimes. So that's why still today in many areas we have people very expert in the dairy, in the food, etc., and they know which is the range of temperature of pressure that you have to operate for reaching some transmembrane flux. Temperature is not a mistake because here we are assuming that everything is at constant temperature. If you change temperature for this kind of system, this parameter is changing diffusivity, viscosity, all these transport property of your solutes, and that will change the history, will change also desorption phenomena. So temperature is not a parameter that you have to redesign the system if you're working at different temperature. So let's start now to see what is just membrane fouling, which I told you is related to concentration polarization, but totally different in the overall mechanism. You can have the origin of membrane fouling, just fouling, is just adsorption and deposition of materials present in the feed on the membrane, leading to some decay in efficiency of the separation, the overall separation process. So you see here, we don't have the creation of concentration profile in the solution related to the intrinsic properties. That means water is going through and the retainer species have to back diffuse, etc. That's totally different. It's adsorption, deposition, etc. So it's much more chemistry and not just fluidodynamics, etc. You can operate in a different way when you work in pressure-driven membrane operation at constant transmembrane pressure and constant transmembrane flux. And in both cases, if you don't control fouling, you can have a significant reduction in permeate flux, additional resistance that's being created, and you can also have change in the transmission of the solids. You can change the selectivity. Rejection can be different. Also the same when you are working in overall constant transmembrane volume, not flux, you can have the increasing in the transmembrane pressure, pressure drops changing. If you will never see this big of plant, you will see there is always an automatic system that is just changing, controlling continuously the pressure drops in the system, different between the pressure in the entrance and the exit or across the membranes, because that's giving you an idea if something is happening. If during the process you form a cake, you're increasing the pressure drop, and the manometer are telling you at which point you must operate, otherwise the system will break down. So you can also, in this case, increasing transmembrane pressure, significant increase in transmembrane pressure, and you will have changes in the selectivity of your solution. So the effect can be significant on the performance. This is the overall design that you have to have in mind when you're talking about this kind of operation, because as function of time, when you are measuring, this is true for ultrafiltration, microfiltration, reverse osmosis, transmembrane flux as function of time is always given by this kind of representation. Just pure water, constant transmembrane flux with time. When you're starting to work with a solution, what is happening that initially, for a relatively short time, that can be few minutes, less than 1 hour, 2 hours, you can observe a small but significant flux decay, but after a short time it's becoming constant. This is what we call concentration polarization. That means this is the formation of the concentration profile in the solution. But after forming the concentration profile, you go to steady state. This is an equilibrium between what is moving convection to the membrane surface, back diffusion in the solution that you can change with steering or axial velocity, but shortly, normally you arrive to this kind of observation. Small flux decay, but concentration polarization will give you a steady state. But what is very often happens that after this initial decay, you don't reach this kind of situation, but you have this kind of situation. So the flux is going down and down with time, and that is fouling. This time, the range of time here, can be, for example, hours. If you're talking about hours, this is okay. That means in 1 or 2 hours, you observe some concentration polarization. In 24 hours, 30 hours, you observe membrane fouling. What you don't observe here is membrane biofouling. There is another kind of fouling, the most dangerous one, the one that we still don't know how to control at the best, which is not given by this. It's given by similar plot where you can have this phenomena after 1 month, after 6 months, after 1 year. So initially, you don't see anything. And that is a trouble because biofouling in the first steps, in the first weeks or months, nothing happened in terms of transmembrane flux, in terms of selectivity. Something can happen, we will see why, in terms of months or years. And when it happens, and you observe, because now you see immediately something is wrong, so you try to solve the problem. You can increase the steering, you can increase axial flow rate, you can reduce concentration, or reduce pressure, we learned already. But when it's after 1 or 2 years, it's complicated because at this stage you have some phenomena of concentration polarization eventually or fouling inside the membrane itself. And it's too late to make anything. So that's the one that still people are working, spending time to understand, because here in this country, in Korea, there are people, many organizations in Seoul working exactly on biofouling to try to understand better what is going on. The problem of fouling is that there are many different kinds of mechanisms. And you can have an external fouling, but you can have also an internal fouling, particularly when you are working in ultrafiltration and microfiltration, or nanofiltration also. In reverse osmosis, normally, what you have is just external fouling, and the fact that people today are realizing plant of producing millions of cubic meters of fresh water per day means, and that means they invest millions and millions of dollars to realize this plant, means that normally fouling is under control. If you have some fouling, somebody has been doing mistakes. Fouling in the big plant in reverse osmosis is relatively easy to be controlled, and is normally just external fouling. And an external fouling is just the origin of increasing the effective membrane thickness eventually, but you know how to solve it just by appropriate control of the flow dynamics. All the plant, also in a row, are working with some fouling, often with some, small level of fouling, or small levels of concentration polarization, but this does not affect too much the overall performance. So the cost is, you lose something, but there's no big trouble. When the fouling is internal, the trouble starts. The external fouling normally is in ultrafiltration, in microfiltration, is given increase of the thickness, can have, if you have porous membranes, not at all obviously, but porous membranes, you can have blockage of some pore. Something can be just blocked physically, the pore, and you can just reduce the size of the pore. So that can be this kind of effect. The internal fouling is when you have the same kind of phenomena, absorption, deposition, but within the pore. And in this case, the hydraulic permeability and the selectivity are just modified for internal blockage of the pore, internal reduction of the pore. So these are the most typical situation that you can realize. How you can try to predict or understand what is going on in your plant. The easiest system that people have been trying to use is related to trying to develop a model, what is called a resistant in series model. You are assuming in principle that all these kind of phenomena, blockage of the pore, constriction of the pore, formation of additional layers, etc., are just additional resistance to the overall system. It's not just the membrane itself, with its thickness giving a problem, but is something more that happened during the operation. And so you can have just to define and to identify the different additional resistance that can be formed in your system. And depending from your level of accuracy, capability, you can just have in simple membrane resistance and the fouling resistance, just two terms that just is an easy way to define your system. But these RF, the fouling resistance, can be subdivided, if you are smart, in 2, 3, 4 different effects that can create the overall fouling phenomena. And it depends from you, the capability to identify or to subdivide the overall fouling in these different effects. We will see some of them. But the way to analyze analytically system will be just a series model, one by one in series. The overall fouling can be here considered in first approximation splitted in two processes. The cake fouling, just having origin suspended particle that just form a cake layer on the membranes, or the little bit more complicated one, the absorption of, that can be also small molecules, it's not a question of the size, etc., absorption of small molecules and soluble material on the membrane surface and the membrane pore. This is the one that, for example, can be very much related to the fact that your membrane is charged, is not charged, is hydrophobic or is hydrophilic. So depending from the interaction between the species, the solutes, and the chemistry of your membranes, you can have different level of absorption, desorption, or formation of the blocking inside or on the surface of your membranes. And that's why you can just consider that you have to add in the resistance series model the effect of the overall fouling related to the membranes, and you can subtract the initial one that you measure with just water, and so between the difference between the two, it will give you the resistance you can attribute to the fouling. So the total resistance after your experiments minus the initial one made with water give you an overall indication of the effect related to this overall fouling. As I was mentioning, that is the way in which can, the analogy with electrical circuit, in which you have these different factors, and is in part related to the traditional Darcy law that people have been using also without membrane but normal filter. And you have the volumetric flux is proportional to the driving force, delta P, and at the denominator, you have the different kind of resistance that you can have in your system. And that is just a little bit more than just the overall fouling. You can see here that you have a resistance related to the membrane itself, to the what happened on the membrane surface, what happened in the pore. So each one of these resistance, if you're able to measure it, is giving one contribution to the overall problem in the system. This is a little bit still more complicated. So these people have been able to define in this resistance series model the initial membrane resistance, easy to measure, but after you can have resistance caused by absorption of the foulant species, just one resistance related to the concentration polarization phenomena, which is not fouling, that's why you can calculate independently. You can have resistance related to the reversible fouling caused by, for example, a very weak interaction of the foulant, which can be eventually removed by washing or backwashing. You can have irreversible, and that's the problem that we were discussing before, caused by strong attachment of foulants, and producing pore blocking, cake, gel, biofilm, and this is not easy to remove by at least stirring or physical methods. This is the most critical one, and in some case, if some solution, something happen, no way. If you have made mistakes to operate in this situation, at the end your membrane has to go to the garbage. There is no way to recover it. That's why, remember that in all membrane operation, there is always a pre-treatment. We are talking about ultrafiltration, reverse osmosis, etc. They never work by itself. When you go to reverse osmosis, before arriving to the reverse osmosis module, there is a significant, what we call pre-treatment. Cost of the pre-treatment in the running operation is about 60% of the overall cost of your process. So the cost of the pre-treatment can be more expensive than just the cost of the RO itself. Because if you don't do this, your membranes have to be changed very quickly. The overall cost we will discuss later are the costs where pre-treatment and eventually today also post-treatment are already included. Because this is an intrinsic cost. You cannot, if anybody is telling you that you can operate with no pre-treatment, don't trust. It's a truck, it's just telling stories. You always need more or less severe pre-treatment, but always is necessary because in some case, with the pre-treatment, you can avoid this kind of irreversible fouling phenomena. You learn what is attaching your membranes, you learn what is destroying the membranes, and it's much easier to remove from the solution before arriving on the membrane than just destroy the membrane itself. So the pre-treatment is essential and is to control this kind of fouling phenomena. In all this talking, I was telling that there is no osmotic phenomena. The correct expression, in fact, is not the one that we were looking before, but this one. Because in principle, when you form a gel layer or a cake or you absorb something, you can induce not only an additional resistance, but also you can induce some osmotic phenomena. That means your membranes can have some selectivity to the small chemical species that we're going across, or you can induce some high concentration of high molecular species also, the same gel, and that is induced osmotic problem. Remember that the osmotic pressure is nothing more than is the same equation than gas equation. That means osmotic pressure is proportional to the concentration of the solutes multiply RT, etc., which means that if you have a big protein, high molecular weight, normally the osmotic effect are very low. And that means because the concentration is very low if there's high molecular weight of the species. In this case, normally you can neglect the osmotic phenomena related to high molecular species. But if you just gelify, that means you're approaching the saturation, the phase inversion system, that can be also an effect on the osmotic pressure related to high molecular species, not only to the small one. For sure, if you have an additional film that has some selectivity for sodium, potassium, small ions that are normally going through the membranes, that's what the case I was mentioning before in ultrafiltration dairy industry, people were not expecting any problem on the transmembrane flux related to the change in concentration of small species, because in ultrafiltration you have rejection 0 for sodium chloride and potassium, you have only rejection for the protein. But if you form an additional film on your initial ultrafiltration membranes, this film can have an effect on the sodium chloride present in the solution, also if the membrane was ultrafiltration, and that's changed the situation. And it happened many times before people were understanding. So in this case, if you have a more general equation, you have to assume that the driving force is not just the difference in pressure, but it's P minus pi, minus the osmotic pressure. This term in some cases can be neglected, but in some other cases has to be considered. And so when you see something that you don't understand, don't neglect to consider this kind of phenomena that can be at the origin of the problem you are considering. Basically, this is the situation that when initially you have this kind of situation in which you have your closed flow and you are working against the membrane with a certain resistance, you assume your film model, that is the boundary layers in which you have laminar flow, And so you can make your calculation, but you can also have another situation in which you can have the initial membranes plus this additional film that you form. If you have this, now also the concentration profile are changing. Over this concentration is not more the same. You can have, that was the initial one, but now you can have another one that can be totally different interfacial concentration here, related to the effect of this additional film where osmotic pressure can be significant. So if you do this, this can be much more effective. And people were making mistakes. People were assuming that this decay in the transmembrane flux was just related to the film, to the model before, to the series resistance. So they were changing to reduce this, in terms of pressure. It's not. That is the case. The origin was osmotic problem. It was not problem of to be reduced with film. So that has to be just, you have to understand which is the real mechanism controlling the phenomena, basically. And the osmotic phenomena can be significant, so you have to take care of what is happening in this new kind of configuration, and the new interfacial concentration can affect the pressure, the driving force to the system, basically. I was mentioning before, remember these parameters, and that will explain why. When you're talking about concentration, we have the dilute solution, ideal behaviors, concentrate solution is different, your ideal behavior is not more present. However, when you're talking about concentration, don't speak only in terms of concentration as you are used. Molar concentration, number of mole per liter, or molality or molarity, etc. This is another parameter which is very important in this kind of operation, which is the ionic strength. The ionic strength of your solution is kind of, that is not, this term is the one that gives you the possibility to understand what is activity coefficient. It's a real term giving you deviation from ideality. If anybody made an experience in electrochemistry, and if you've been studying the Debye model that gives you the real configuration of electrolyte solution, you will learn that any ions is always surrounded by clouds of a charge opposite to the charge of the central ions. And this is the real situation that you have in a solution. Ions don't exist by itself. They just are ions plus a cloud of charge opposite to the sign of the ions. And if you just develop this model, you understand deviation from ideality related to this kind of morphology that you have in the system. The parameter that is giving you some, at the end, some information is the ionic strength, which is nothing more than this overall, the addition of all the ions present, Ci, but they compare in this not only in terms of mass, molality, etc., but mass multiplied for the square of the charge they have. So this is the real parameter affecting the overall behavior of your solution and changing from ideality to non-ideality, because you can understand here that, for example, the fact that this charge is present and it's present with the square root at the end of, if you understand the Debye model, is telling you that you can have a significant difference in the behavior between monovalent and bivalent, for example. And also this parameter is the one that can affect the performance of your solution in terms of space configuration. Because when you have a change in protein, for example, depending, globular or linear, final morphology is just related to the interaction or repulsion of the different segments of your protein, whether there are positive species or negative one. And this will reorganize completely the space configuration of your protein. And is related not to the concentration, is related to the ionic strength. Is related to the concentration multiplied for the square of the charge of the single groups. So this parameter is the important one, and that's why in some case we have to recall, and it's better you remember, when something is not clear, remember that is not concentration effect, it's a ionic strength effect. That means concentration multiplied for the square of the charge for the single ions. And that can change significantly the story. Before, we have been discussing a little bit about fouling related to any kind of simple compound, can be electrolytes, can be high molecular species, can be a protein, etc. There is one fouling that is the most terrible today for us, still not well understood, and still present, and that can kill your process sometimes, which is biofouling. Biofouling is a fouling, as the term, related to the effect, the interaction between biomolecules and the membrane surface. Typical example in the most part of the solution, the water we are treating, river water or also seawater, brackish water, seawater, there is always some organic compound. Typical example is a humic acid. And this system have a complicated chemistry that slowly, today, people are studying to understand how this chemistry can affect our membrane performance. It's not just the presence of humic acid. It's the fact that humic acid can easily interact with metals present in the water. And depending from the metals, you can have different kind of behaviors. Simple case, you can have this humic acid interacting with sodium. You can have a very kind of weak interaction forming this kind of complex. And this kind of system can deposit or interact with membrane surface. What is worst, and that is for each kind of organic species and each kind of ions, you can have the formation of not weak interaction between the different substances, but strong interaction forming real new chemical compounds, as in this case, and they can significantly interact with the membrane surface, not in the form of sodium and humic acid eventually with relatively weak chemical bonding, but as a new complex. And this is the one that can interact with the membrane surface and creating problem. At the origin, what is called also biofilm. Biofilm is something that happens everywhere. In our body, we have a lot of biofilm. Some of our diseases sometimes are just related to the creation of biofilm in some part of our system. So biofilm is complicated. What is worst, that in some cases is not just adsorption or desorption. What is happening is that when you have, particularly in microfiltration, in ultrafiltration, but also in reverse osmosis, you can have initially in your system some bacteria, some microorganisms, few of them. After microfiltration, after pretreatment, everything is clean. You can drink the water, no big problem on your health, etc. But still you can have 1 or 2 or 3 of these bacteria present somewhere, or they can penetrate somewhere. And what's happening that when initially they go on the membranes, and they can be blocked on the membrane, also physically, because, for example, in RO, they cannot go through. It's a dense membrane, no way to penetrate. The same can be in ultrafiltration. They can be deposited on a pore. And initially, nothing happened, because on your big membranes, there is one bacteria blocking one pore, or just reducing a small surface available in RO. Nothing happened. Your flux is still constant, basically. But these bacteria, if they are related to some kind of microorganisms which are still active, they live on the membranes. They can start to eat and to use membranes itself or some of the nutrients which are present around for growing and producing and developing something that at the end became a film. And when normally it happens, this film is already, they start to live and produce what is called mucoglucosaccharides. This term here, that is EPS, extracellular polymeric substance, which are also biosubstance normally. Mucoglucoside is one of the most traditional terms. And when these things happen, you can have some simple bacteria that can be associated with some of these extracellular polymeric materials. And they have a complicated, you must be a microbiologist to understand what is going on. They can interact in a very strong way or in a very weak way with the membrane surface and this complicate life of these things. You can have detachment, decomposition. You can initially accumulate and after you just redecompose. But basically, they live on your membranes. Initially, when there is only one or two of this, no big problem. Sometimes they are one or two. But when they start to accumulate and penetrate and produce some more of these extracellular polymeric substance as this mucoglucoside, they can go in the membrane itself. At this point, you see something. Flux decay is still going down, no more constant, and there's nothing to do. You have to take your membranes. There's no way you can increase axial velocity or steer more, etc. Big washing, nothing. Take the membrane, put in the garbage, and put a new one. And these things don't happen shortly. They can happen after 1 year, 2 years. Biofouling can appear also after 3 years. And when it appears and you realize there is biofouling, you are losing 20% of your capital investment because you have to change the membrane. You cannot recover anymore. On the contrary, it's possible the recovery when the just normal fouling or concentration polarization we learn is reversible, so there's no problem. But normal fouling, normally you can clean. There is a different way. You can clean chemically, you can clean physically, etc. But with biofouling, you can do nothing today. In the sense, we don't know how to do it. We will see that how these people are trying to understand more, and some progress has been done, but still we don't have any real standard solution. When you're doing this work, you have to try to measure the quality of the water that in principle at least is not giving fouling. So you want to be sure, because I told you that 60% of your pretreatment is to avoid any fouling in ultrafiltration and particularly in reverse osmosis. Again, it's not easy to predict and to evaluate scientifically what is going to happen in the system, because the system are so there are so many variables. You can have different concentration, different species, etc. However, some standard way to predict if your system will be under fouling problem or not exists. One of these is what is traditionally was called the Silt Density Index, SDI. This way has been standardized worldwide without really understanding what membranes are, but people accepted the idea that there were some numbers. When this index is lower, normally about 3, 4 in some case, that means a value between 0 and 2 or 3, the water in principle is good for going, for example, to traditional RO membranes. When it's higher than 3, 4, you must have a problem. You have to improve your pretreatment and so on. This was the previous index that has been accepted. As you can see here, this is ISTM standard methods, classified D4189, very famous. We are trying from long time to change and to make something better than this, but still today, the most accepted and the most standardized at international level is the 4189. So you have to follow this one in principle when you make your contract and you ask to the company to pay or not penalty because the system does not work. You have to respect this salt index, otherwise you are guilty because your pretreatment was not good enough. This index is defined as the capacity of water all these numbers are standard numbers. Everything has to be done in a certain way. You have to use a membranes with microfiltration initially, 0.45 micron, at a pressure of 30 psi. And the equation that you have to respect is this one. SDI is 1 minus T1, T2 divided T per 100, where this T is the total elapsed flow time. T1 and T2 are times measured in seconds, required to filter 500 milliliter of water initially and after T minutes respectively. As you can see here, very, very standard, because that's the way you can compare between one system and the other if you are using all these parameter standards. And normally, this is critical. This kind of experiment is done in a dead-end filtration. And we have been learning that normally you don't work in a dead-end filtration. So that's the first point. We have to change this because normally you are working cross-flow filtration, why you have to define the silt index in dead-end filtration that you are never using. And that is one of the problems. And with a continuous flow under pressure, the membrane has to be put perpendicular to the permeate flow, dead end. And the total time is shown. The standard time normally is 15 minutes. And the sample flow during the filter during the entire 15 minutes. And the water flow through the membrane, fouling will continue to accumulate, and at the end, you have this difference between T1 and T2. This is the most legal one. That's why you have to follow the law. That is, you know, ISTM is the International Association for Standard Methodology. So that's the organization recognized from United Nations that define which are the standards and the way to define any parameters. Some changes been introduced one by one. Today we have already the modified fouling index, the MFI, and the MFI, where there are these two relationships that you have to define, is the volume is recorded every 30 seconds, again for a period of 15 minutes, and it again you can measure in constant pressure or constant flux. And again, this same parameter is the same. There's one more parameter that is changing, not only these 30 seconds, but this is 2 bar, and viscosity is 20 degrees centigrade, A is the membrane surface, and that is the same kind of microfiltration membranes is present. This is a little bit improvement, because just for changing the time of recording, etc. However, there is still a little bit better than this, because first of all, with this kind of standard modified field index or traditional one, as I was mentioning, the range you can operate is that for what concern the SDI, traditional, from 0.2 in reverse osmosis, 0.3 in nanofiltration. In the modified F1 is 0.2 in reverse osmosis at 0.10. That's in nanofiltration. So if you respect your value of this index lower than these numbers, in principle, when you buy a plant, they give guarantee that the system works. But they will check that you have been able running with a pre-treatment that was giving water to the plant in this order. And this is registered. If they found that at one time your SDI was 5, and you cannot complain anymore, because they tell the origin of the problem is your fault because you are not being able to pre-treat in the right way your membranes. So you must be careful to check continuously and to avoid to overcome this limit. That's why people today, there's a lot of legal action in the world during the last years related to where was the origin of the problem. And that's why people are trying also to modify the index, introducing, for example, cross flow and not dead flow, which can make a significant difference. Changing the membranes. Instead of using all these two, we have 0.45 microfiltration membranes. This is many chemicals, low molecular weight, organic species particularly, can go through these membranes, and they can affect, at the end, the performance of URO, for example, as it was with biofouling. So today there are tentative, not successful until now, to have not only this 4819, what it is, but have a new standard, well accepted international level, much more sophisticated than the previous one, in which, for example, we have no more microfiltration, but you have nanofiltration, ultrafiltration membrane, you have UF membranes, much more narrow in pore size, so you can select better, and you can work not in dead flow, but you can work in cross flow, approaching much more the real operation that we have. This big story that is going on is not yet accepted, but basically the system that is written here, the 0.45 has to become something different, and then let's see if we have definite, we don't have the number, but anyway, today you can make the same kind of operation is done in this modified, remodified silt index, in ultrafiltration and more microfiltration, in cross flow. Instead, then again here you have to define time, accuracy, etc., etc. But these systems are a little bit more complicated, but much more appropriate for doing this evaluation of the quality of the water before entering your RO system, particularly that is the most important case, okay? Some of you will be involved in the future because this is an open field and it's not only science, but it's also marketing and the interest of the company, how to define the best index to evaluate the quality of the water entering your membrane. And when you invest billions of dollars in a plant and you know that the operation is related to the quality of the water, it makes sense to have some parameters that you well understand, you can well measure. How to control normally the concentration, polarization, and fouling, and possible subsequent fouling, we already discussed a little bit. Turbulence promoter is a way of doing, and there's different kind of turbulence promoter, by the way. You can have artificial turbulence promoter, that's something that you include in the system, but some of the membrane today in operation have intrinsic turbulence promoter. If you read literature, you'll find some people from Toray company. Toray company claims that their membranes are the best because at the membrane surface, at nano level, at molecular level, they have some protuberance, a kind of small protuberance just on the surface, and they claim that the good performance of their membranes related to this protuberance, which are acting as internal turbulence promoter. Each one of these protuberance, when the fluid arrives, is creating some vortex, and that is a way to enhance at molecular level the efficiency of the system. You can have corrugated membrane surface, which approach the idea of the protuberance of Toray. You can have some now external effect. For example, you can have a pulsing of your solution entering the system. Pulsing means that the concentration profile and the level of concentration, you never approach the critical transmembrane flux, because the profile is always, you just stop before arriving to a critical value. So you can have a pulsing system, or you can generate a vortex. You can invent a way to generate vortex, or you can just have a two-phase system. You can blow inside, and that's typical for membrane bioreactor, we will see. Bubble of air. So this air is entering the system and is creating better steering and reducing of the problem. That is one of the best methods at the end is the backflushing. Not all the membrane can operate with backflushing. Backflushing means that here you have normal in ultrafiltration, microfiltration, in some cases nanofiltration, you can have your solution running inside your tube. This is capillary membrane, for example, and you can accumulate something on the membrane surface, particularly if you have some particle in suspension, etc. Now, what we can do at this point, when this thing is becoming severe and you have flux decay, so when you are starting to, you have your transmembrane flux, the function of time, you start to go down, and if you don't do anything, down, 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 and you will arrive quickly to foul your membrane completely. What you can do, that after a certain period, and that's something you have to do by yourself and learn, depending from your solution, which is the value, every second, every half an hour, every 5 hours, you can backflush. Some of the water was coming through, you move on the other side and you pulse inside through the pore. That means and the frequency of this backflushing, something that everybody has to learn by himself, depending from the quality. At the end, instead of having this kind of behavior, you will have this behavior. Well, you just have the backflush, flux is going up again, and will start to go down, and if the frequency is the appropriate, at the end, you will keep an average value of this kind, and it will never arrive down here. This is very well utilized today in most part of ultrafiltration and microfiltration system. And it works very nicely. You spend some money because you have to backflush, you spend some energy, you lose part of your permate because you are using 2, 3, 5% of your permate to backflush, but you can operate in this way without destroy the separation. Let's go back a moment to biofouling, because again, also this does not work for biofouling. It works for any traditional fouling, but not for biofouling. Biofouling can be eventually minimized with this technique, etc., but if something happens at the end with the external polymer that you are producing, etc., you kill your system. I told you, you have to lose all your money for changing the membranes. there is different, more sophisticated way to protect, particularly for biofouling. One is that if you are able to increase, for example, hydrophilic character of your membranes, or depending from the kind of interaction that exists, or the kind of bio compound which are present, you can functionalize the membrane surface, in general just making more hydrophilic is the right way of doing, by chemical treatments. You can have coatings or just functionalizing. You can induce some carboxylic group or some aldehydic group, etc. And you can create some situation in your traditional polyacrylonitrile membrane, for example, where you can block some amino acid or something on the surface. That will decrease the possibility of interaction, eventually creating some repulsion for the species at the origin of the fouling. What is more interesting today, however, by the way, if you are doing this, this is the overall, the end of the story where we are now today. If you have to decide how to pre-treat your membranes, and in terms of the, forget about the chemistry we saw before, but about hydrodynamics, here are different results that are existing today. You have dead-end filtration, enhanced cross flow velocity, bubbling, that means the two-phase, backflushing, and air bubbling. You can see here that the best way of doing today is this one up here, which is just backflushing and eventually with air bubbling. The backflushing and air bubbling combined are giving you the best results in general in many other situations. So you can just summarize with the existing methodology. This is down here, backflushing air dispersion is the best way of doing compared to the traditional other way of doing. So if you really want to solve your problem, today you have to spend money to realize backflushing and eventually this bubbling air dispersion in the system. Again here, this is the result that you can have in terms of chemical treatment. Chemical, there is a lot of pre-treatment just to clean your membrane chemically, and there is different kind of solution that has been tested. Now, what you have to use in this case, this is a fouling, you have to interact with this species that have been absorbed. So ADTA complexing agents is a typical case. SDS is another case, typical case. SDS is the sodium methylenediamine triacetate, that is the ADTA. The sodium dodecyl sulfate is the other chemical. And you see here that these are the most traditional one in terms of cleaning efficiency, and that is just a different function of this chemistry is different depending, for example, the pH of the solution. The behavior and the complexation and decomplexation depend from the ionic strength or pH of the solution, for example. So, but today, the most utilized are complexing agent as a DTA or this SDS. And here, again, this is for membranes cleaned by organic fouling. There's organic and also inorganic fouling. Anyway, there's the same kind of result for everybody. The one I was looking is the new approach where people are making research today and how you can try to minimize not the traditional fouling that most part can be solved, but the biofouling. And there was an interesting idea originated here in Korea, not too far from here, in the National Seoul University, where there are researchers that they learned, they were chemical engineers, but trying to understand the mechanism of fouling formation, biofouling formation, they arrived to the point, interesting, telling them, for having a biofouling, that means for forming a biofilm, if you have one bacteria initially present, one or two, the biofilm cannot, the origin of the problem is not one or two. It's the fact that one or two become 1 million or become 100,000. So they grow. For growing, everything, in all the systems we know, we have to communicate. These bacteria, they have to communicate between one with the others. They have to recognize one to the other, interact, and start to proliferate and to live together. They have to make a colony. So one way to avoid this is why don't we try not to destroy the bacteria, but to avoid the communication. Let's try to block the possibility of these bacteria to interact and talk each other's and recognize each other's and starting to grow. for a chemical engineer, that was something strange. It seems to be an electronic approach, etc. And in fact, it is an electronic approach. That was the way to block the communication between different single molecules and try to block the growth of the biofilm. Quite interesting, because it can solve this problem, but can solve a lot of problems in biofilm formation, which are related to our life, as I was mentioning already before. So it's now your knowledge in chemical engineering is only a small part of the story. You have to become very quickly a good microbiologist and very advanced microbiologist, able to control the communication between different microorganisms when they grow, etc., etc. Some people decide to do this, and so they found that there are some species which are the one that can block communication. This story of these quorum sensing materials is a way to avoid. Now, there are some of the species that are harmless type, aggressive type, etc. And that everything, all the phenomena are function of the population density that can be at the origin of the propagation and growth, etc. But now, for what we are concerned, people realize that you can, if you identify for each kind of wastewater, this kind of microorganisms which are present and the chemicals that are at the origin of the communication, if you can entrap in some beads these chemicals which are the origin of the communication, so you can produce these cell entrapping beads, cells, with a porous microstructure by entrapping quorum quenching bacteria, this Rhodococcus PHBH4, in alginate beads, and this can be utilized in your system to see if this, if the choice was correct, and the logic is correct, to block the growth of this microorganism in this kind of situation. And that is what happened. If they made this, they realized that using on the membrane surface these beads created in this way, this was with no beads was present, and this one the beads were present. So they've been able to block the communication between these microorganisms and to avoid the formation of basically the biofilm, which is the origin of the system. This is nothing, is not yet utilized. You see that the people doing as a typical Korean names, and there is 2 or 3 groups working a lot, and today there are meetings only on quorum quenching, quorum sensing, etc., because it's appearing one of the most interesting new approach to try to realize this kind of situation. These terms are in the same, after the same period of time, etc., etc., and apparently it works. You have to learn still a lot, because the problem here that is not the same for each kind of waste. Each kind of waste can have different, if you are going on municipal wastewater or you are going in dairy industry, probably you have to find different kind of quorum quenching, quorum sensing, chemical, etc., but the mechanism can be at the origin. So the concept is not trying to destroy or to remove, etc., trying to avoid the communication between the different bacteria so that they not proliferate and they don't create a colony. They stay by themselves. They will be very boring for them. Then nothing will happen, and they cannot block your membranes. Still part of the research activity in progress, but quite interesting area of research I was mentioning, because if you're interested, you can go and talk with your some professor here in Seoul, and they will explain in detail what is going on. There's been a meeting a few weeks ago, months ago, in Gunsan, only devoted to this, with 100 people taking part. And there's nice proceedings. If anybody interested, ask to the proceedings of this last meeting, and you will find a lot update information on this line of activity. Quite interesting. Just a few comments to finish with this part of our program. First of all, how we utilize our membranes. Simple system, and we're talking, you have different possible to put together your module. One is just use batch process. We don't like. Very unusual that we are working in a dead flow and batch system. Membrane operation, one of the interesting advantages, we are making everything continuous process, moving from batch system to continuous system. That is one point that's very important for process engineers, basically. And that's why this is, but in some case, for example, in some fermenter, sometimes you're still necessary to use a batch system. But in general, at least you're going always to continuous system. That means, as we discussed many times, you can just cross-flow on the membrane surface and you apply your driving force across the membranes, but you just go to cross-flow, and now you know why, because doing this way, you can always try to keep the concentration at the interface equal to the one in the bulk to avoid concentration polarization, to avoid formation of cake or gel, etc., to avoid all the concentration and fouling problem. However, working with one module is not sufficient, obviously, and you can, and also this configuration is still one of the possible ones. For example, you just have this feed and bleed process, some cases where you can just reutilize part of your retentate. You can separate and reutilize in the circle, etc. And you can have that dia-filtration. You can keep constant, in some case, the concentration of the solution on the membrane surface when you arrive at a certain level by re-injecting some solvent to avoid more increase in the concentration. That's called dia-filtration. That's important when you want to recover as much as possible your retentate, not the permeate. If you have antibiotics, very expensive, or antigenis, or what it is, and here there is also a dead volume at the end, in which there is still in the retentate some of your antibiotics, a lot of money sometimes. So what you can do, if you increase more, if you want to increase the recovery factor, you cannot do, because you create fouling, you can have concentration polarization too high, and the solution, the system does not work anymore. What you can do, when you approach the limit value, the limit of the concentration before precipitation, saturation, you start to inject inside an amount of solvent equal to the amount of solvent you extract. So the concentration does not increase anymore. But in the what you extract, you can still extract the chemicals of interest. So you just extract 100% and not 50, 60%. The negative aspect of doing this way, you dilute a lot your permeate. So what you extract is much more diluted because you are putting more solvent in. But if the cost analysis will tell you if convenient or not. If the added value of the concentrate is high, it's some just very expensive chemicals, you can just do it, dia-filter. That's another configuration similar to this feed and blade. Obviously, when you have to work with 3 million square meters of membrane installed, it's not one or two modules that you have to operate. There are 30,000 modules, 45,000 modules in some plant. In this case, it's no more the job of chemists, etc., the job of very expert chemical engineers or process designer who are able, what you want to do, this is a modular system. Modular means that you are assuming, and which is true, that for each of the modules that you have in your system, the properties for obtaining the right performance are the same in terms of entrance pressure, in terms of output, the pressure drop in a single module, etc. For doing this, you have to try to combine at the best the module. You can do putting some stage in cascade, in series. What is going out from stage 1 is becoming the feed of stage 2 and so on. Or you can put together in parallel and in cascade different tracks. So you can have, in this case, these are in parallel and these are in series. And again, this configuration is giving you the possibility to treat in a modular way. That means without all the module will have the same parameters at the entrance and at the X, basically. When you have 30,000 on this module, system is a little bit more complicated, and it's not our job, but there are people who know how to put together 30, 45,000 module, huge one, to obtain the same performance, roughly the same performance, of all of them as expected by the one that you have for one of them. And that's quite interesting, and only membrane engineering can do this kind of job. No other system is able to optimize in this way. If you want to scale up a traditional MSF, etc., no way that you can realize something similar today. That's why that's one of the most interesting aspects of the membranes. Last few points, where the energy consumption is coming in our membrane operation. Basically, the total energy that necessary for realizing your separation in using membranes is based on at least 3 different parts. The first is the energy required for the transport of the filtrate from the feed across the membrane. That is the driving, the number one. The second one is the energy necessary to pump the feed filtrate solution through the membrane module. That's the one to arrive to the membranes, and that's the one that you have to move across. First is the energy required for the pre-treatment and post-treatment that you have in your system, and all the energy necessary for all the instrumentation and so on. Now, this last one basically is negligible. You can not take in consideration, it's not too severe, and except some special case in which the pre-treatment is very expensive. But the one that we have to consider is basically the one that we are using to move the chemicals across our membrane. That is the real value. Now, this is the Gibbs-free energy we already discussed in reverse osmosis or in nanofiltration, in other process, that the Gibbs-free energy of mixing, that which is the minimum energy required for the separation of the component of the mixture, is the real term that we have to calculate. It is a reversible term. It can be obtained when the retention and filtrate solution are mixed together. Let's also remember is the term that we will utilize when we will talk about blue energy, because it's this Gibbs-free energy of mixing is the one that, if you can try to use in the appropriate way, can be transformed in mechanical energy and finally in electricity. And blue energy is exactly this kind of difference before mixing, and when mixing is just disappearing, having an homogeneous solution. The energy required to overcome the friction between transport component and the membrane matrix is the other component we have to consider, and this is the irreversible term. This is the reversible part of the overall energy. This is the irreversible part. This is what we call energy loss. Basically, this is lost. There is no way we can recover and reutilize. The equation giving us this kind of term are already familiar to you. Basically, we realize that the differential of this Gibbs-free energy of mixing in temperature and pressure constant, and just function of the concentration of the system in the membrane system is just given by this expression where you have the activity across of the solution, the two faces of your membranes. And that is what we really utilize, and that can be rewritten in terms of osmotic pressure difference. That is a real term that we have to overcome, which is a part of the of our in the reverse osmosis we learn very quickly, and that is you can also at the end rewrite all this and giving that in terms of integral form. The delta G of the Gibbs-free energy of mixing is nothing more than delta pi multiplied for the feed molar volume. So that is basically the term that we have to overcome. Now, the total energy that you have to utilize for the filtration is for the real separation is the one given by the effective driving force, which is the delta pi. This is written with sign different than the one we used last time. Anyway, same story. This is the effective driving force, delta pi plus delta P. That means hydrostatic pressure applied to the system to overcome the delta pi that's moving the water in the other direction, multiply for this total permeate volume. This is related to the permeate volume. Delta pi, the osmotic pressure difference. E is the energy required for the real separation. Delta P FR is the pressure loss to the friction, the one I was mentioned before, with the membrane matrix. PF and PP, feed and permeate pressure. Overall, this is a very ideal expression because nothing works in this as written here. In the sense, first of all, the membrane, this is, you can write in this way, assuming, for example, rejection equal 100% selectivity, which is not the case. And the efficiency of the system, everything is 100%. It's not. So the equation that we are describing is true only say, if we have a recovery rate, 100% of recovery rate, all the system is working with a recovery rate of 100%. We know that we are working 50%, 60% already. And that's why in real application, we have to introduce some coefficient to make more real this expression. These are the coefficient we are measuring. Basically, the delta that we have to introduce here is the recovery rate. 50%, 60%. If we improve the system using, for example, membrane distillation, that can be 95%, and that can be quite interesting. But today, this delta is 50, at most 55, 60. That's the efficiency also for the recovery of the energy we're using. That's an important part of the story. One way to reduce the overall energy consumption today is to develop not membranes, but the system for energy recovery. System for energy means because when you pressurize your solution, you are working at, you apply 50, 60 atmosphere on your solution on the membranes. The permeate is 1 atmosphere. So you're losing, at the end of the story, if you don't find a way to recover the excess of pressure still present in the system, you're losing a lot of energy. So what you have to do, you can recycle part of your retentate, still pressurize, using, for example, a Pelton turbine that can just recover part of this pressure. And the turbine will create energy that you can reuse in the plant. Or pressure exchanger. Pressure exchanger are a new system, not turbine, in which you can still recover it better than the Pelton. Pelton was done for a huge plant, and not for the kind of plant that normally are reverse osmosis. Today, maybe the Pelton can also be competitive, but one time it was not. So we have to just have increasing the efficiency of single units. So delta and this the K is also the efficiency of the turbine that you are introducing for the recovery of the energy. Basically, if you have to pump in the system, this is the energy that you have to consider. And also in this case, you have to introduce the efficiency of the pump, which is not 100% normally. So there's another deviation from ideality for the driving for the thermal pressure. Basically, this is the kind of parameter that we have to control. And today, there's a lot of efforts in improving not just the membranes, but this kind of parameters for changing the cost. And here you can find, keep in mind that the overall cost at the end, considering this kind of analysis, a function of the driving force, the applied hydrostatic pressure, is not linear. And that's another key telling you a lot of work has to be done. Chemical engineers, membrane engineers are working to identify this minimum, which is not obvious and not easy. The reason for this minimum here, that's very important in terms of cost, is that when you increase hydrostatic pressure, obviously you're just, for example, decreasing the membrane cost. Increasing hydrostatic pressure in principle, assuming that there is no concentration polarization, you are just reducing the membrane surface necessary. So you are decreasing the overall impact of the cost of the membranes on the system. Energy cost obviously is increasing if you're increasing the hydrostatic pressure. Maintenance cost is also relatively decreasing when you're increasing the pressure, but if you add these three terms at least, assuming that you made the right calculation with the right coefficient, etc., here is the minimum. So if you're working at a higher pressure, the energy is increasing significantly with no motivation. So we have to identify where you are. And that is not easy, and more today we are learning how to do better. If you look here, where are the costs, the overall cost? As we saw before, the real cost is electricity. Electricity means the cost for pressurizing the system and moving the chemicals across your membranes. The cost of the membranes, remember, is relatively low. People sometimes are telling, we need better membrane to reduce the cost of the system. Membranes are too expensive, etc. What are you talking about? Membranes, at the most, and today are still decreasing, they have an impact on the overall cost of 7%. These plants are billions of dollars sometimes, or 100, 500, 1,000, not 1,000 of millions of dollars. That means that the real cost is much more in all the rest and not in the membrane. Membranes, if you just increase, you can reduce. Yes, but not for sure too much, because it's no more than 7% of the cost. And this cost is still decreasing because the cost of the membranes are decreasing. Real cost is here, in the electricity you're using. That means what you have to do is to develop a system better designed than the traditional one. And eventually, you can combine this with some of the consumables which are still not marginal, much more than the, is not consumable per se, are the one that you are the cleaning, you have to control fouling and pretreatment. These are overall costs. And this is the point where you have to work. If you understand how to control, if we will avoid biofouling using this nice microorganism communication block, we will reduce this cost together with electricity, and that will be quite interesting. The cost of electricity can be reduced in two ways. One is to reduce, for example, the pressure we have to utilize, the efficiency of the pump can be increased, etc. But the other one is to reuse as much as possible the electricity. And that can be done just using energy recovery device. And these are the most important. The one that exists today, initially were just these energy, the turbine or the Pelton turbine, where you can just recovery. Part of the, the solution was arriving at 75 bar in here. And you have on the perme side is 1 bar. So you have a delta in the pressure of 75 bar, which are lost if you don't recover. If you recover, putting a turbine here, part of this energy, not 100%, but part of this can be recovered, if I remember, 60 or 70, and that will be utilized again in the system. Recently, another way of doing, not a turbine, but what they call a pressure exchanger has been introduced. The same story. Initially, the pressure exchanger were much better than the turbine. Today, the plants are becoming very big, and the efficiency of the Pelton turbine has been modified and increased for this application because a new market was appearing. And so now the competition between the pressure exchanger and turbine is a little bit, it's not clear which one of the two, depending from different situation, you can choose. In some cases, better the Pelton, in some cases, better the pressure exchanger. But this is a field where there's a lot of progress going on. You can see here the difference in the cost. That is depending from the cost of the energy. Energy is the factor number one, as we saw. 40% of the overall cost is energy, is electricity. Now, the cost of electricity is not the same around the world. If you go in Saudi Arabia, very low cost because they burn everything, they burn oil, no problem. If you come to Italy, it's very high, and the same in some other country. So depending from the cost, you have different cost of the water you are producing. Does not depend from the cost of the membrane. We learned membranes is 8%, 7%. Cost, the real cost, 40%, is the cost of electricity. And roughly, today, when the electricity is cheap, you are working around less than 0.5, 0.6 cents of a dollar. For this is an euro really, but cents of a dollar, I remember the number in dollar, than for a cubic meter, for 1,000 liters. So quite interesting number. But the cost depends also from the reuse that you can have. You can see here using a Pelton turbine, here you can gain about 20, 30% in the cost at the end. And that's particularly when the cost of energy is increasing. And when you compare the same story for the different kind of recovery system, pressure, that is the turbine, and that is the pressure exchanger, the efficiency still is in kind of 41% against 45, if I remember, 48. So there's still competition. It's not big difference, but this is an area where every day we have progress. When you go next meeting of IDA, in the Desalination Society, you will find better pressure exchanger, more efficient Pelton turbine, and that's what can make a very real difference on the final performance. Let me use still 2 minutes, so we close this session, and we will not discuss more about what is exergy. Until now, we are talking about energy, energy, energy. Forget about energy. You have to learn more and more that when you make this kind of evaluation, what you have to consider is not energy, is the real part of energy that you can utilize in your making your work, which is not energy, is exergy. Normally, the total energy is also formed by exergy and energy. Now, energy is the part of the energy that is forced to be given to the environment as heat in condition of complete degradation. Lost is irreversible. That is part of the energy. And sometimes you just assume that you can recover, reuse, etc. Forget. This is the part that is going, is irreversible. What we really are interested, where we can improve the system, is the component which is exergy. Still, many departments in chemical engineering, when the secretary is making some report and typing, if you write exergy, she make a correction, you put N, say, well, what you're talking about. She does not have to correct. Exergy exists, and more people has to become expert in how to calculate not just energy, but from energy to calculate exergy. That means to calculate what are called the exergetic loss of the system. Because if you identify where the exergetic loss are present, you can identify where you have to put your money to improve the energy quality of your system. And that is not a question of the energy, it's a question of the exergy. So for doing this, the definition of exergy is that part of the energy that by reversible transformation can be completely converted from one form to another, which is not the case of the energy. Therefore, energy can be defined as the maximum amount of work obtained by the evolution of a system with reversible transformation from the initial state to the equilibrium state with the environment. Keep in mind that this is particularly important, the definition, when you are not looking to the single units, RO, when you are looking to the system, because this system, as you can see here, depends very much from the term of reference, depending from what happened upstream and what happened downstream, what is the temperature upstream and what is the temperature downstream, the exergy can significantly be changed. And that's why when you're looking not to a single step, just the RO, just the centrifuge, just these sedimentators, but you're looking to overall system, including pre-treatment, including post-treatment, this kind of analysis is quite important. For doing this, what you have to calculate are the entropic losses, which means you have to know exactly in your system all the different parameters. You have to know about the electrical energy, exergy supplied to the cycle, to the thermal supply to the cycle, the difference between the two, and you can calculate for each one of these terms the exergetic losses. When you know the exergetic losses, you have a lot of real interesting information. Because you can realize, for example, that makes no sense to change, I don't know, the pump, because you have to change the valve. Because the lamination valve is the place where your exergetic losses are the highest. So forget about the pump where you lose 10% and go to the other part where you lose 90%, etc. That normally you don't know because you have an overall energy consumption and you have no idea where you have to put your attention more. So there's nothing new except this more accurate understanding of the quality of the energy, which means to use not only the first principle of thermodynamics, but also the second one, because that is what we are doing. We are the quality of the energy necessary is what the exergy is telling you. In principle, you have to do more than this, because if you want to really analyze the benefits of this kind of technology compared to the traditional one, and they are very, very different, you cannot, very often, you cannot use anymore the traditional metrics that people have been using until now. We are teaching to our students and to our younger colleagues making research to use new metrics appropriate with definition of process intensification. Because process intensification is the umbrella under which we are making all this kind of work. But in process intensification, the metrics are different, the understanding of the problem are different than in traditional one. For example, we are not talking anymore about mass. We are talking about mass intensity. That means the ratio of the total mass with the mass of product. We are not talking about energy. We are talking about energy efficiency, total process energy divided in mass of product. We are talking about ecotoxicity that people were never connecting to the energy consumption. Today, eco problem is a cost. If not considering the environmental impact, the eco-environmental factor, at the end of the story, the cost of your product will be 10 times higher than the one you are considering. So you have to start to make your calculation introducing ecotoxicity, introducing waste intensity, introducing safety. Safety is a cost today. In the past, there was not. A good company was investing in safety. The other one was bad, was not investing. Today, you cannot start a new operation if you don't spend money in safety. So this is a real cost, exactly as electricity. It's exactly as the cost of the land. So it cannot be neglected in the overall calculation. Today, very often, people don't consider safety a cost. Safety is a cost, exactly as electricity. And the economy says, so all these new metric, and more than these are coming. We also introduce what we call flexibility, for example, modularity. All these parameters, typical of process intensification strategy, are real costs that has to be considered and introduced, particularly when you develop this new kind of operation. And here they are some of them. We call this productivity, productivity system compared to the size of the plant. Productivity compared to the weight of the membrane, that is productivity compared to the load of pollutant emissions, etc., flexibility, etc., etc. Okay, so you will find more and more these kind of units. Okay, with this we stop for the moment. We have been covering until now, quickly, I have to say, much more quickly than because we have just half the time available, but the pressure-driven membrane operation. From next time, we'll start to talk to different kind of membrane operation, the electrochemical membrane operation. Fuel cell, our electrochemical membrane device, blue energy or electrodialysis. And following, we will cover other kind of membrane operation, membrane contactors, membrane distillation, membrane crystallizer, membrane dryers, membrane condenser, membrane emulsifier, etc. Okay? Thank you.